Okay, welcome back, volume of simple surfaces. And so this basically is an introduction to volume in calculus, and we'll just get you started about. We'll let you see how you can actually go about doing volume and how it actually makes sense. Once again, this is an introductory video, so there aren't going to be any example problems. I've been doing that a lot for the area and volume things, just because it's so important to be able to visualize what's going on. And so I just want to take some time to draw graphs. And so let's get started. This is about simple surfaces only, although, I mean, we'll talk about some of the underlying concepts for volume, which will apply to everything. But particularly, this is about simple surfaces, so I mean, basically three-dimensional solids that there are no gaps, no holes in the middle or anything like that, and they're obtained by revolving two-dimensional graphs around axes, around either the x-axis or the y-axis, not any other line. It has to be the x or the y-axis. That's my definition of a simple surface. So let's get to this. So when to use it? Well, guess what? Area wasn't enough. Now we got to talk about volume. So one of the coolest things that we can do in Calculus 1 is this. Revolving a 2D graph about a line to create a 3D surface and calculating the volume of that new shape. Which is kind of crazy to think of, but this is an awesome technique that allows us to find the volume of lots of different solids. So this video, I'm going to just give you a formula for finding volume of solids that contain no holes or hollow spaces revolved around the x or the y-axis. That's how you get these surfaces. I'm going to give you a formula and explain to you how it works and why the formula is as it is. And then in the next video, I'm actually going to do some example problems so you can get some practice. But this is just to show you why we can do it. So one of the things that your teacher, if your teacher has already maybe gone over this topic already, she's probably mentioned the fact that, well, it's kind of difficult to visualize a lot of these three-dimensional solids because, well, I mean, you're drawing a three-dimensional solid on paper or virtual paper like me. So, like, trying just to depict three dimensions, trying to show three dimensions on two dimensions, it's obviously difficult. So, especially like we can draw cubes and stuff, right? That's not that difficult. But when we're trying to draw really complicated shapes that we don't see every day in the real world or anything like that, or they're not that popular, then that's when you start to realize, you got some. This is when it starts to get really difficult. And so, like in your textbooks, your textbooks are a great source for diagrams and stuff, or graphs of surfaces or 3D solids, right? Because they use computers to generate those things. Whereas your teacher and me, I'm drawing these things. I'm drawing these things with a pen. So we got different methods of arriving at our graphs, but hopefully you should still get the idea. That's the point, and that's I think you will probably do that. So looking at the graph at the top, I want to put an emphasis on this. This is like maybe half a parabola, right? And what we do here is we're going to revolve this around the x-axis. Crazy. So imagine taking the two-dimensional graph and going around the x-axis. So everywhere the two-dimensional half of that parabola there, everywhere the curve goes, it leaves like rabbit trails, so to speak. It leaves trails of it. And so when it finally reaches where it started, it has created this three-dimensional solid that is symmetric about the x-axis. And so you have like the parabola at the bottom and then parabola at the side. The problem, as I said, is it will be hard to depict, to draw these, especially in a short amount of time. That looks really messy because I also use this. I use the same color for the revolving line. That is why when you see my three-dimensional solids, usually I'm gonna have graphed them already. I'm gonna have drawn them already prior to recording the video, so I don't have to waste time actually drawing them. But this is what you would get. It's kind of like what would you call like a megaphone, I guess, a megaphone shape. You know, the thing that you talk into and makes you louder. Kind of like that kind of shape here. Simply because we had our half of the parabola, and then we took, and as we revolved it around the x-axis, we got a half of the parabola over a half of the parabola like in the same plane as the x-axis. Then we got right below the x-axis, and you got another one in the same plane, and you got all these different places where the parabola is, and that's why we have all these and that's how when you put them all together, we've had this megaphone shape, so to speak. So I'm just going to present to you the formula for finding the volume of a simple solid like this. And there are two formulas actually, and this is where it might get a little confusing with all the words here. But the two formulas that you see here, very similar to the area formulas, in that you're going to put a function in for your radius. So for the radius that you see there's going to be a function, like an f of x, g of x function. And there's a dx difference, a dy difference between these two formulas. Also the a's and b's for each formula. Well, for the top formula, the a's and b's are going to be x values because you're going to plug them into the antiderivative of that, which is going to contain x values because dx. So you're integrating with respect to x. So the a's and the b's are x values. For the top one, the a's and b's for the bottom one are y values. So basically, when we are revolving a curve, just to make it simple, when we're revolving a two-dimensional curve around the x-axis to produce a three-dimensional solid, and they want us to find the volume, we use the top formula. We use this formula. The one with the revolve about x-axis thing here. When we are finding the volume of a solid that's generated by taking a two-dimensional curve and revolving it about the y-axis, we use the bottom formula. So I have it lined up here pretty simply. But just to look at the general idea behind this formula and why it works and how you are going to use it when you do one of these problems. So this is the general formula. So what does this actually mean is what my point is. Well, this actually makes a lot of sense. We're going to approach this the same way that we would approached area, which was when we took a look at our shape, we just split it up, right? That's what we do in calculus. One of my calculus professors says, what we do in calculus, we divide and conquer, which makes a lot of sense, actually, because we do a lot of splitting up shapes into small parts. We can't actually directly find the volume of this whole megaphone thing, right? So, or loudspeaker or whatever. So, we have to split it up into lots of different shapes in order to get there. Hence divide and conquer. So that's what we did for area, and we're going to do the same thing here for volume. Now, if you think about it, if we were to divide this megaphone up into lots of different spaces, so now we have like when we divided an area up into lots of different spaces, we got lots, like if we have, for example, really quickly, like that's our little thing, and then this is our graph, right? When we divided up area, we got these little rectangle shaped things, or whatever. They were little areas that then we could compute, doing a base times height thing. The base was dx, or yeah, in this case dx, or dy, but in this case that'd be dx. The base was dx, the height was your function, f of x. And so that was how you actually got the area of one of these areas. That's how, or one of the shapes, the two-dimensional shapes. That's how you got the area using f of x times d of x. F of x represented the height, d of x represented the width. And then, so you would compute this for every single shape to get all the different areas, and then it was the integral that actually added them up, and then you did it over a certain region, right? Because that would be like A, and this would be like B, or whatever, right? And so that's what you did with area. So for volume, we do something very similar, except for volume. When we split this up, you know what I notice? When we split this up, we get lots of mini three-dimensional solids. So instead of splitting this, when we split up the area and we get these, when you split up when we're doing area and we do the splitting up and we get lots of different areas, right? Lots of small areas that then we can add up using the integral. When we split this up, we get lots of different 3D solids. We get all these parts of the megaphone. Imagine taking a megaphone, like maybe like a styrofoam megaphone or loudspeaker, whatever you call it, and taking like a knife and chopping up the megaphone. You get little mini pieces of the solid, three-dimensional things, and so you'd be finding the volume of these three-dimensional things and then adding up. That's what we're going to do. Find the volume of the little itty-bitty three-dimensional things and then adding them up. Well, it turns out if you split them enough, really close, if the solids, the small solids that you create are so small, right, infinitesimally small, we're still using that word, then you have little itty-bitty cylinders. If you split up the loudspeaker small enough, then you'll get these really small, not cylinders in the sense cylinder. Cylinder actually is a very good term. And so, how do you find the volume of a cylinder? The volume of a cylinder, right? It's pi r squared times h, right? Well, in this case, if we're finding the volume of each itty-bitty cylinder, they really don't have any width. Keep that in mind. They really don't have any width because they're infinitesimally small. And we're splitting this up into we're splitting the megaphone up into an infinite number of small three-dimensional solids. So they don't have any width. Imagine just a bunch of lines, all throughout the megaphone. These don't have any width. And so you could think of the, super incredibly small width as the height. You can think of the super incredibly small width that you find in each of those solids as the height. And if you did, then you could represent that as dx or dy or whatever. And if you represent that as the width, then you take care of the h. What about the pi r squared? How are you going to write the pi r squared in calculus terms so that we can do this? The pi r squared, well, you could put the pi, that's a constant. R is simply just the radius. So you need just some form of the radius, square it, and then integrate it. The integral meaning adding up all the different solids you have here, all the different ones you have here, adding them up, until you get the total volume. Add up the parts, you get the total. And that's what we are going to do for all of our volume problems. It's going to take this general form. And so that is actually what I have written here. So the two match up. Now you probably wonder, okay, but what's the radius? How do I find out what the radius is? It turns out that the radius of your cylinder is simply oftentimes just the function. Oftentimes it's just the function. So when I take one of these super small cylinders, and I have, I can't draw an incredibly small cylinder, so, let's pretend this is super small. That's my super small cylinder. For the purposes of this, well, actually, it's probably a poor way of drawing it, so I'm not going to draw like that. But you get the idea that for the height, we called the height as the height of our cylinder. There was the width. So basically, it was like this. Actually, we're like this, and that was the height. But you pretend like there's, it's very small height. And then the radius is, well, you have a circle there, right? You have a circle there. So the radius is just the radius of your circle, the base of the cylinder. Like you could pretend that's the circle. So the radius is just whatever. But in this case, if you think about the radius would just be this. That's the radius. And in that case, that's just whatever the function value, the y value of the curve is. And so, in most cases, for a simple surface, the function value, the height, is actually just the function, or the radius, really. Right? The radius, we'll call it the radius, because we have it all like turned on its side. The radius is actually the function value. So you could kind of write this as just as an f of x, so to speak. As it relates to simple surfaces, then you get the crazy stuff like when you have two-dimensional curves and then you revolve both of them around an axis. And then that's all like, that's a little more different because then you have to deal with two functions. But for a simple surface, the radius is simply just one function. Okay, so yeah, these are the formulas. We can call these disks, by the way. It's just a disk method of finding the volume when there's no holes or hollow points or anything like that inside your thing. Your textbook might call it disks, or your teacher might call it disks. Look at this amazing problem. We're going to solve it in the next video. Okay, there you go.